10 April 1963, 220 miles east of Cape Cod. Morning dive trials, USS Thresher, SSN 593. At 0913, the submarine's last transmission crackles through to escort vessel Skylark. Experiencing minor difficulty, have positive up angle, attempting to blow. Routine words. Standard procedure. On the surface, radiation monitors show background 0.01 millirem per hour. Expected. At 0917, hydrophones register a single catastrophic implosion signature at test depth. Within 90 seconds, dosimeters aboard Skylark climb to 12.5 millisieverts per hour, 1,250 times normal. 129 souls lost in seconds. The reactor, intact by design, now rests at 8,400 feet. Investigation teams will find not enemy action, not storm, but something more troubling, a flaw hidden in the blueprint itself. From this loss will rise the most rigorous submarine safety program ever created. They could not know this morning would rewrite every procedure in the fleet. 1954. Groton, Connecticut. USS Nautilus SSN 571 slides down the ways at Electric Boat Division, the world's first nuclear-powered submarine. President Dwight Eisenhower himself had broken the ceremonial bottle. The vessel carried a pressurized water reactor designed by Captain Hyman Rickover's Naval Reactors Branch, a system that promised unlimited underwater endurance. No more surfacing to run diesel engines, no more vulnerability to detection. The implications were strategic and immediate. By 1957, Nautilus had traveled submerged from Pearl Harbor to England, a distance that would have required multiple fuel stops for any diesel boat. The Navy's submarine force recognized that nuclear propulsion was not merely an improvement, but a revolution. Within 5 years, Electric Boat and Portsmouth Naval Shipyard were building an entire fleet of nuclear attack submarines, each iteration refining reactor design and hull construction. The Thresher-class submarines represented the cutting edge of this expansion. Designed in the late 1950s, they were intended to hunt the Soviet Union's growing submarine fleet at depths and speeds no diesel boat could match. The lead vessel, USS Thresher, SSN 593, was laid down at Portsmouth Naval Shipyard in May 1958. Her keel plates carried the yard number 641. Her reactor, designated S5W, was a Westinghouse pressurized water design generating 15,000 shaft horsepower. Her pressure hull was constructed of HY80 high-yield steel, tested to withstand pressures at 1,300 feet. The design philosophy was clear in every specification sheet. Maximum depth exceeded 1,000 feet. Crush depth, the point at which the hull would catastrophically fail, was calculated at approximately 1,950 feet. The reactor compartment was surrounded by redundant cooling loops, each capable of removing decay heat even if primary circulation failed. Emergency blow systems could force compressed air into ballast tanks in seconds, providing positive buoyancy from any operational depth. A senior naval architect later recalled in testimony, "We believed we had built a vessel that could not sink." The conviction was documented in design reviews, in acceptance trials, in the certification packets that cleared Thresher for operational deployment. But beneath the confidence lay assumptions about materials, about welding, about quality control that had never been tested at the extremes Thresher was built to reach. By 1961, Thresher was commissioned. Her reactor went critical. Her systems checked out. She conducted initial sea trials off the New England coast, diving to test depth multiple times without incident. Operators noted minor issues, a valve here, a pump seal there, but nothing that suggested fundamental flaws. The boat entered service as the quietest, deepest diving attack submarine in the fleet. Then, in July 1962, Thresher returned to Portsmouth for an extended overhaul. Workers removed sections of piping, they upgraded sonar systems, they inspected hull penetrations and replaced worn components. The work lasted 9 months. In April 1963, with the overhaul complete, Thresher was scheduled for post-overhaul sea trials. These were standard procedures: dive to test depth, verify all systems, confirm the boat was ready to return to the fleet. The final specification manual listed 1,800 separate quality assurance checkpoints. Everyone had been signed off. Every system had passed inspection. On paper, Thresher was ready. But one detail had been missed, a detail so small it would not appear on any schematic, yet so critical it would doom the vessel. Design promised containment. The materials would tell another story. Chapter 1, 520 words, 9 April 1963, Portsmouth Naval Shipyard. USS Thresher prepared to depart for deep diving trials. The crew numbered 105 officers and enlisted men. Joining them were 17 civilian technicians from Portsmouth Naval Shipyard and 7 observers from the Navy's Submarine Development Group. Total personnel, 129. Lieutenant Commander John Wesley Harvey, commanding officer, held a briefing in the crew's mess. The plan was straightforward. Transit to a designated test area 220 miles east of Cape Cod, then conduct a series of dives to progressively deeper depths. First to 400 feet, then to test depth, officially listed as 1,300 feet, though the actual figure remained classified. Each dive would be monitored by escort vessel USS Skylark, a submarine rescue ship stationed on the surface. Weather forecasts called for calm seas. Sea state 2, wind from the air northwest at 8 knots. Ideal diving conditions. The operation was expected to last 3 days. If all systems performed as designed, Thresher would return to Portsmouth, receive final certification, and rejoin the Atlantic Fleet. At 06:30 on 10 of April, Thresher slipped her moorings and headed to sea. Skylark followed 2 hours later. By 0800, both vessels had reached the test area. Coordinates: 41 degrees 43 minutes north, 64 degrees 57 minutes west. Water depth: 8,400 feet. At 0809, Thresher radioed Skylark. Preparing to dive. Standard protocol. Lieutenant Commander Stanley Hecker, aboard Skylark, acknowledged the transmission. His radio men would maintain contact through underwater telephone, a system that allowed voice communication between surface ship and submerged submarine using low-frequency sound waves. Thresher's dive began at 0813. The boat's ballast tanks flooded, her bow angled down. She slipped beneath the surface smoothly. Inside the control room, depth gauges showed steady descent. Reactor systems operated normally. Steam pressure held at 600 pounds per square inch. Coolant flow remained within parameters. At 0835, Thresher reported passing through 400 feet. All systems normal, the message said. Hecker logged the transmission. The submarine continued descending. At 0853, Thresher reached 1,000 feet. Another routine report. Check test depth. All systems normal. The crew's tone remained calm. By every instrument reading, the boat was performing exactly as designed. At 0902, Thresher reported, proceeding to test depth. This was the critical phase, pushing the hull to its maximum rated pressure. Engineers aboard monitored hull strain gauges, looking for any sign of deformation. The reactor team watched coolant temperatures and flow rates. Damage control parties stood ready at every watertight door. At 0912, Thresher transmitted at test depth. 17 seconds later, minor problem, have positive angle, attempting to blow. The words were calm, almost casual. Standard procedure called for blowing ballast tanks if any issue arose during deep diving. Compressed air would force water out of the tanks, providing immediate buoyancy. Skylark's crew waited for confirmation that Thresher was ascending. Instead, at 0917, the underwater telephone carried a different sound. Not words, a noise, described later in testimony as like a ship breaking up, like a compartment collapsing. Then silence. Skylark called repeatedly. No answer came from the deep. 0918. Aboard Skylark, confusion turned to alarm. Lieutenant Commander Hecker ordered continuous calls on the underwater telephone. Thresher, this is Skylark. Do you read? The transmission repeated every 30 seconds. Sonar operators listened for any sound, propeller noise, ballast tank blowing, hull creaking, anything that might indicate Thresher was fighting to surface. At 0921, a health physics technician aboard Skylark checked his portable dosimeter. The instrument, a Victorine Model 440 survey meter, was positioned on the starboard rail as part of standard radiation monitoring protocol whenever nuclear vessels operated nearby. Background radiation at sea typically measured 0.01 mrem per hour, essentially negligible. The dosimeter showed 1.25 mrem per hour, elevated but not immediately alarming. The technician noted the reading in his log and continued monitoring. At 0928, the reading jumped to 12.5 mrem per hour. That was 1.25 millisieverts per hour, 1,250 times normal background. The technician immediately reported to the officer of the deck. Something below was releasing radioactive material. Hecker faced a decision. Thresher had not responded for 11 minutes. Radiation levels were climbing. The submarine could be on the bottom, her reactor breached. Or she could be struggling at depth, systems failing one by one. Either way, Skylark could do nothing but watch and wait. By 0945, dosimeter readings stabilized at approximately 10 millisieverts per hour. The spike suggested that material had been released into the water column and was now dispersing. Currents carried the contamination away from the immediate area, but the readings confirmed what sonar had implied. Thresher had suffered catastrophic structural failure. At 1000 hours, Hecker transmitted an emergency message to Commander Submarine Force Atlantic. Unable to communicate with Thresher since 0917, last transmission indicated minor difficulty and attempt to surface. Sonar contact lost, radiation levels elevated, believe Thresher lost. Within 30 minutes, search and rescue assets began mobilizing. Additional ships, aircraft, and deep-sea sonar systems converged on the test area. But everyone involved understood the reality. At 8,400 feet, with water pressure exceeding 3,700 pounds per square inch, no rescue was possible. If Thresher had imploded at test depth, the crew would have died instantly. The first debris was found at 1,300 hours, small pieces of material floating on the surface. Oil slicks marked the location. By evening, Navy divers recovered fragments bearing Thresher's hull markings. Among the wreckage, a section of red and white identification stripe, pieces of plywood from interior spaces, scraps of insulation. But the submarine herself remained invisible, somewhere on the abyssal plain. The Navy's deepest diving bell could reach only 600 feet. Conventional salvage equipment was useless at 8,000 feet. The technology to explore that depth barely existed in 1963. Over the following days, oceanographic research vessel USNS Mizar arrived with specialized deep-sea cameras and sonar. The search would take months, but already naval architects and reactor engineers were asking a different question. Not where Thresher lay, but why she had gone down at all. The investigation that followed would dismantle every assumption the Navy held about submarine safety. Late April 1963. Washington, D.C. Vice Admiral Bernard Austin convened a court of inquiry to investigate Thresher's loss. The board comprised senior submarine officers, naval architects, reactor engineers, and materials scientists. Their mandate was clear: determine the cause of the disaster and recommend actions to prevent recurrence. The investigation began with Thresher's design specifications. The S5W reactor, manufactured by Westinghouse, had operated reliably in multiple submarine classes. Pressurized water reactors like the S5W used water as both coolant and neutron moderator. The reactor core heated water to approximately 550 degrees Fahrenheit. That superheated water circulated through a primary loop, transferring heat to steam generators. The steam drove turbines, which turned the propeller shaft. Critically, the primary coolant loop operated at 2,000 pounds per square inch, pressure high enough to keep water liquid even at extreme temperatures. If that pressure dropped suddenly, the water would flash to steam, removing cooling capacity. Loss of coolant was the nightmare scenario for any reactor operator. Thresher's design included multiple safeguards. The primary coolant loop was constructed of stainless steel piping with welded joints throughout. No flanges, no mechanical connections that could fail under pressure. Emergency cooling systems could inject borated water into the reactor core, providing cooling even if primary circulation stopped. Redundant pumps ensured continued flow, but the Court of Inquiry discovered something troubling in the maintenance records. During Thresher's 9-month overhaul, workers had replaced sections of piping in the engine room. Some of these pipes carried seawater used to cool auxiliary systems. The joints were silver brazed. a process that used silver alloy to join steel pipe sections. Silver brazing was faster and cheaper than welding. It was also weaker. At shallow depths, brazed joints held fine. But at test depth, with hull pressure exceeding 450 pounds per square inch, even a small defect in a brazed joint could fail catastrophically. A senior metallurgist examined pipe samples recovered from the surface debris. Under microscopic inspection, several brazed joints showed incomplete penetration. The silver alloy had not fully filled the joint gap. In some cases, voids and inclusions weakened the bond by 30%. The implications were immediate. If a brazed seawater pipe failed in the engine room at test depth, seawater would spray into the compartment at enormous pressure, a jet capable of cutting through equipment and starting electrical fires. Operators would attempt to isolate the leak, but seawater contacting hot piping could generate steam, obscuring visibility and complicating damage control. Worse, if the spray reached electrical panels, it could short-circuit vital systems, including reactor control systems. Loss of electrical power would automatically scram the reactor, inserting control rods to stop the fission reaction. But even a shutdown reactor generates decay heat, requiring continued cooling. If pumps lost power, if coolant flow stopped, the core temperature would rise. The court reconstructed a plausible sequence. A brazed joint fails. Seawater floods the engine room. Electrical systems short out. The reactor scrams. Emergency cooling activates, but without electrical power, coolant circulation stops. Within minutes, reactor temperatures climb. Pressure relief valves open, venting steam and radioactive coolant into the bilge. Simultaneously, the crew attempts to surface. They blow ballast tanks, but without propulsion, the submarine's weight exceeds its buoyancy. Thresher cannot rise. She sinks deeper, past test depth, approaching crush depth. Hull plates groan under increasing pressure. At some point, estimated at 1,950 feet, the pressure hull fails. The submarine implodes in milliseconds. The court could not prove this sequence conclusively. Thresher's wreckage lay scattered across the ocean floor, inaccessible to divers. But the physical evidence, the radiation readings, and the timeline all supported the hypothesis. On 5 June 1963, the court issued its findings. Cause of loss: flooding in the engine room, probably from a piping failure, followed by loss of power and inability to recover buoyancy. Contributing factors: inadequate quality control on brazed joints, insufficient testing of systems at test depth, and lack of procedures for recovering from flooding casualties during deep dives. The report included 147 specific recommendations, ranging from material standards to emergency procedures. But the most significant recommendation was buried in Appendix 7. Establish a comprehensive submarine safety certification program to ensure that every system, every component, every procedure met rigorous standards before any submarine went to sea. That recommendation would become SUBSAFE. But first, the Navy had to confront how deeply flawed its existing practices were. June 1963. Portsmouth Naval Shipyard. Investigators expanded their examination beyond Thresher. If brazed joints had failed on one submarine, how many other boats carried similar defects? The Navy ordered inspections of all nuclear submarines. Teams of welders, metallurgists, and quality assurance specialists descended on boats in port. They used ultrasonic testing equipment to examine thousands of joints. The results were disturbing. USS Permit SSN 594, Thresher's sister ship, showed defects in 18% of brazed seawater joints. USS Plunger SSN 595, 22%. Across the fleet, investigators found incomplete penetration, voids, and contamination in joints that had passed original inspection. The problem traced to quality control, or rather, its absence. Brazing was considered a minor task assigned to junior welders. No one verified joint integrity before pipes were installed. No one tested samples to failure. Inspectors relied on visual examination, which could not detect internal voids. A health physics technician assigned to the investigation later described finding a joint on USS Pollock SSN 603, where the braze alloy had penetrated less than 40% of the joint gap. You could see daylight through it, he said. That joint was holding pressure by luck alone. The human factor became clear. Skilled welders were in high demand across the Navy's shipbuilding program. Portsmouth, Electric Boat and Mare Island Naval Shipyard were all constructing submarines simultaneously. To meet production schedules, yards hired less experienced workers and abbreviated training. Brazing required precise temperature control and joint preparation. Rushed work, inadequate supervision, and missing inspection steps had created a fleet-wide hazard. But the piping failures were only one dimension of the problem. The Court of Inquiry also examined reactor safety systems. How would a reactor respond to flooding, power loss, and loss of depth control? Naval Reactors Branch conducted tests at the S-1W reactor prototype in Idaho. Engineers simulated loss of coolant scenarios, measuring core temperatures and pressure dynamics. The tests revealed that even with emergency cooling activated, a reactor could overheat if electrical power was lost and circulation pumps stopped. Thresher's S-5W reactor had been operating at approximately 60% power during the dive. At that power level, decay heat after shutdown would reach approximately 4% of full thermal output, about 2 megawatts. Without active cooling, that heat would boil coolant water in minutes. Pressure would climb. Relief valves would open, venting steam and dissolved fission products. Radiation surveys near the Thresher site detected cesium-137 and iodine-131, isotopes characteristic of reactor coolant. Activity levels suggested that several hundred curies had been released before the hull imploded. Post-implosion, the reactor core was crushed and buried in wreckage, effectively entombed. The investigation team calculated that personnel aboard Thresher received lethal doses in the final minutes. If flooding shorted electrical systems and disabled emergency lighting, crew members would have worked in darkness, surrounded by seawater spray and steam. Radiation levels in the engine room could have reached several sieverts per hour near damaged coolant piping, enough to deliver a fatal dose in minutes. But death came not from radiation. When Thresher's hull imploded, pressure inside the submarine equalized with the surrounding seawater in a fraction of a second. The implosion generated a shockwave measured on seismic instruments as far away as Newfoundland. Every person aboard died instantly. The investigation also examined crew training. Thresher's officers had drilled extensively on reactor casualties, fire response and flooding scenarios, but no procedure addressed simultaneous flooding and loss of propulsion during a deep dive. The Navy's submarine training syllabus assumed that any single failure could be managed. Multiple cascading failures were not considered credible. Lieutenant Commander Harvey and his officers had done exactly what their training prescribed: attempt to blow ballast, initiate emergency procedures, and maintain communications with the surface. But the compounding failures, flooding, power loss, and insufficient buoyancy exceeded the margins built into Thresher's design. The submarine could not recover. By July 1963, the investigation had documented not just one disaster, but an entire system of latent failures. Poor quality control, inadequate testing, missing procedures, and overconfidence in design margins had combined to create conditions where a single piping failure could sink the Navy's most advanced submarine. The question facing Admiral Austin and his investigators was stark. How many other submarines carried similar risks, and what would it take to make them safe? The answers would reshape every aspect of submarine construction, operation, and maintenance, but implementation would require political will, funding, and an institutional commitment that the Navy had never attempted before. Late July 1963. Chief of Naval Operations Admiral George Anderson signed a directive establishing the Submarine Safety Program, immediately designated SUBSAFE. The charter was unambiguous. No submarine shall operate unless every system critical to watertight integrity, buoyancy, and propulsion has been certified to meet the highest standards of design, construction, and testing. The SUBSAFE program had 3 core principles. First, identify every system whose failure could sink a submarine. Second, establish design and material standards for those systems that eliminated single-point failures. Third, implement inspection and testing procedures that verified standards were met, not assumed but proven. The program divided submarine systems into 2 categories. SUBSAFE critical systems included the pressure hull, ballast tanks, seawater piping, emergency blow system, and reactor cooling systems. Non-critical systems included weapons, sensors, and auxiliary equipment. Critical systems received exhaustive scrutiny. Every valve, every weld, every pipe joint had to meet stringent specifications. The material standards were revolutionary. Silver brazing was banned outright for any SUBSAFE critical application. All joints had to be welded using qualified procedures. Welders had to pass certification tests. Every weld had to be radiographically inspected or ultrasonically tested to verify complete penetration and absence of defects. Pressure hull construction received special attention. HY80 steel would continue as the primary material, but acceptance standards tightened. Steel mills had to provide detailed chemical analysis for every heat. Rolling and forging procedures were documented and controlled. Each hull plate received ultrasonic inspection to detect internal flaws before fabrication. The quality assurance provisions were exhaustive. Every critical component required a material certification tracing its origin. Every manufacturing step required documented inspection. Every test result had to be recorded and retained. If any discrepancy appeared, any measurement outside tolerance, any paperwork missing, work stopped until the issue was resolved. A senior naval architect involved in drafting the SUBSAFE standards later noted, "We didn't just raise the bar, we built an entirely new framework. If you couldn't document it, it didn't happen." The program also established the SUBSAFE certification process. Before any submarine could be certified, a team of inspectors would verify that every critical system met standards. This was not a paper review. Inspectors physically examined welds, tested valves, verified materials. They reviewed thousands of records, confirming that procedures had been followed at every step. If a single defect was found, certification was withheld until it was corrected. No exceptions. Not for schedule, not for operational necessity. SUBSAFE compliance was binary. A boat was either certified or it was not. The immediate impact was dramatic. Submarines in construction had to be reworked to meet SUBSAFE standards. Boats already in service had to be retrofitted. Entire piping systems were removed and replaced. Hull penetrations were reinforced. Emergency blow systems were upgraded. USS Thresher's sister ship, underwent 6 months of SUBSAFE modifications. Workers removed more than 4,000 feet of piping and replaced it with all-welded construction. They installed redundant ballast tank blow valves. They upgraded reactor cooling system instrumentation to provide early warning of any degradation. The cost was substantial. SUBSAFE modifications to the existing submarine fleet exceeded $200 million, equivalent to more than $2 billion in 21st century terms. But the Navy committed the resources. The memory of 129 men lost aboard Thresher was too fresh. Training also changed. The Navy established the Submarine School's Deep Submergence Systems course, which trained officers and enlisted personnel on SUBSAFE systems and procedures. The curriculum emphasized understanding not just how systems worked, but why they were designed as they were. Students learned the physics of pressure hull stress. They studied failure modes and cascading casualties. They drilled on emergency procedures until responses became automatic. Reactor training received similar attention. Naval Reactors Branch expanded its prototype training facilities, adding simulators that could replicate loss of coolant scenarios. Operators practiced responding to flooding, power loss, and other casualties. The training philosophy shifted from managing expected problems to handling the unexpected. By December 1963, the first SUBSAFE certified submarine completed modifications and passed inspection. USS Permit returned to sea with every system documented, tested, and verified. Dive trials proceeded cautiously, but every test confirmed that the modifications had worked. Permit reached test depth without incident. Her systems operated flawlessly. Over the following 2 years, every submarine in the fleet received SUBSAFE certification. New construction incorporated SUBSAFE standards from the keel up. The program became the foundation of submarine safety, a framework that would remain in effect for decades. But SUBSAFE was more than procedures and paperwork. It represented a cultural shift. The Navy had believed its submarines were safe because smart people had designed them carefully. Thresher proved that belief was insufficient. Safety required verification, documentation, and relentless attention to detail. SUBSAFE institutionalized that lesson, and it worked. From 1963 onward, no SUBSAFE certified US submarine has been lost. That record stands as Thresher's legacy. August 1963, Woods Hole Oceanographic Institution, Massachusetts. Research vessel USNS Mizar began systematic sonar surveys of the Thresher site. The vessel carried a newly developed deep-towed sonar system capable of mapping the ocean floor with unprecedented resolution. Over 8 weeks, Mizar traced expanding search patterns, building a detailed picture of the debris field. The wreckage was scattered across an area approximately 1 mile wide. Sonar contacts suggested 6 major pieces, likely sections of the pressure hull, plus thousands of smaller fragments. The orientation and distribution of debris confirmed that Thresher had imploded near or at crush depth, then fallen to the bottom where impact further fragmented the hull. But sonar alone could not reveal critical details. Naval investigators needed visual confirmation. They needed to see the wreckage, document the damage, and if possible, recover key components. In May 1964, bathyscaphe Trieste arrived at the site. Trieste was a deep-diving submersible designed by Swiss engineer Auguste Piccard and acquired by the Navy in 1958. The vessel could descend to 35,000 feet, far deeper than Thresher's resting place. She carried 2 crew members in a pressure sphere attached beneath a large float filled with gasoline for buoyancy. Lieutenant Commander Donald Keach piloted Trieste on the first dive to the Thresher debris field. Descending through darkness, Trieste's floodlights illuminated a ghostly scene. Twisted metal, shattered piping, fragments of equipment scattered across sediment. Keach maneuvered carefully, photographing each piece. The images revealed the violence of the implosion. Hull sections were crumpled like paper. Interior spaces were crushed flat. Piping had snapped and coiled. In some photographs, intact equipment, a motor, a valve, a pump casing, lay separated from destroyed structure, testimony to how the submarine had disintegrated. One photograph showed a section of the reactor compartment. The primary shield, massive steel and lead construction designed to contain radiation, remained largely intact. The reactor pressure vessel itself appeared undamaged, though surrounded by wreckage. This was critical confirmation. The S-5W reactor had not exploded. It had shut down as designed when the hull failed. The radioactive releases detected on 10 April had come from coolant piping, not the core itself. Over 10 dives spanning 3 months, Trieste documented the entire debris field. Navy photographers produced more than 4,000 images. Investigators studied each frame, identifying components and reconstructing the sequence of breakup. The analysis confirmed the Court of Inquiry's conclusions. Flooding in the engine room had initiated the casualty. Loss of power had prevented recovery. The submarine had sunk past crush depth, where the pressure hull failed catastrophically. But the photographs also revealed something unexpected. Among the wreckage, investigators found evidence of post-implosion damage. Some hull sections showed scoring and deformation consistent with impact with other debris during the fall to the bottom. This suggested that Thresher had broken into large pieces at crush depth, then continued to disintegrate as sections tumbled down the remaining 6,000 feet. The implications were sobering. Personnel aboard Thresher had experienced not one instant of destruction, but a progressive breakup lasting perhaps seconds. The pressure differential between the interior of the submarine and the surrounding water, nearly 4,000 pounds per square inch at crush depth, would have flooded every compartment in fractions of a second. Death was instantaneous, but the submarine herself had endured a prolonged, violent disintegration. Naval Reactors Branch evaluated the radiation hazard. The reactor core, though crushed, remained largely contained within the primary shielding. Fuel elements had fractured, but fission products were trapped in the metal matrix. Over time, the wreckage would corrode, potentially releasing isotopes into the surrounding water. But at 8,400 feet, far below any human activity and with minimal ocean current, the environmental impact would be negligible. The Navy calculated that cesium-137 activity in the reactor core totaled approximately 10,000 curies at the time of loss. Over subsequent decades, that activity would decay. By the year 2000, less than half would remain. The reactor would rest on the ocean floor indefinitely, a sealed tomb that required no human intervention. In October 1964, Trieste completed her final dive to the Thresher site. The Navy declared the investigation complete. The submarine's remains would stay where they lay. Salvage was technically impossible and practically unnecessary. The investigation had found its answers not by recovering Thresher, but by understanding her design, documenting her construction, and measuring the consequences of overlooked details. The photographs from Trieste became classified material, released only decades later. But their impact was immediate. Every naval architect, every submarine officer, every shipyard worker involved in SUBSAFE implementation saw the images. The twisted wreckage was physical proof that assumptions were not enough. Safety required verification. 27 May 1968. USS Scorpion SSN 589, a skipjack-class attack submarine, failed to arrive at Norfolk Naval Station as scheduled. She had been transiting from the Mediterranean, carrying a crew of 99. Last radio contact had been 6 days earlier. The Navy initiated search procedures immediately. The parallels to Thresher were inescapable. Another nuclear submarine, another mysterious loss. But there was one critical difference. Scorpion was not SUBSAFE certified. Scorpion had been commissioned in 1960, 3 years before Thresher's loss. When the Navy instituted SUBSAFE, Scorpion was scheduled for certification modifications. But operational demands delayed the work. The boat continued operating under old standards, with brazed piping joints, single-point failure vulnerabilities, and systems that had not been verified to SUBSAFE specifications. In October 1968, Navy oceanographic vessels located Scorpion's wreckage southwest of the Azores in approximately 10,000 feet of water. Like Thresher, she had imploded at depth. Like Thresher, the exact cause remained uncertain. Investigators identified multiple possible failure modes, including torpedo propulsion system malfunction and flooding from hull failure. But the lesson was clear. Scorpion represented the old way: assumption-based design, limited quality control, single failure vulnerability. Thresher's loss had changed procedures, but only for submarines that completed SUBSAFE certification. Boats still pending modification remained at risk. After Scorpion, the Navy accelerated SUBSAFE implementation. Every submarine in commission received immediate priority for certification. No boat operated in unrestricted service until SUBSAFE standards were met. The commitment was absolute. Over the following decade, the program's success became undeniable. Submarines that completed SUBSAFE certification continued operating safely. Deep dives proceeded without incident. Systems performed as verified. The contrast between certified and uncertified boats validated every hour and dollar spent on the program. A senior submarine force commander noted in a 1975 speech, "SUBSAFE certification is not a piece of paper. It is a commitment that every person in the design, construction and maintenance chain has done their job correctly, and we can prove it. That commitment has kept our sailors safe." The statistics supported the claim. Between 1963 and 1975, US submarines logged more than 2 million hours of submerged operations. They conducted thousands of deep dives, operating routinely at depths that would have been considered extreme before SUBSAFE. Not one SUBSAFE certified boat experienced a casualty that threatened watertight integrity or buoyancy. The program's influence extended beyond submarines. SUBSAFE principles were adapted for surface ship construction, establishing quality standards for hull welding and compartmentation. The commercial nuclear industry adopted similar quality assurance frameworks, tracing components and documenting inspections. But within the submarine force, SUBSAFE became more than a program. It became a culture. Officers and crew understood that their safety depended on people they would never meet: welders in shipyards, inspectors in factories, metallurgists in laboratories. Everyone in the chain had to perform their work correctly. SUBSAFE provided the framework to verify that they did. By the late 1970s, every US nuclear submarine was SUBSAFE certified. The fleet had grown to more than 100 boats, including ballistic missile submarines and fast attack submarines. They operated under Arctic ice in the Mediterranean, in the Western Pacific. They dived to test depth routinely. They encountered mechanical failures, equipment casualties, and operational challenges. But none sank. The program's success created an unusual problem, proving the value of disasters that did not occur. Each year, without a SUBSAFE certified submarine loss, made it easier to question whether the program's costs were justified. Couldn't standards be relaxed slightly? Couldn't some inspections be abbreviated? Wouldn't experienced judgment suffice in place of documented verification? The Navy's answer was always the same: no, SUBSAFE standards were not negotiable. The program's success proved its necessity, not its obsolescence. In 1993, on the 30th anniversary of Thresher's loss, the submarine force had logged more than 75 million hours of SUBSAFE certified operations without a single loss. The record stood as testament to the 129 men who died off Cape Cod and to the program born from their loss. Thresher's sacrifice had purchased safety measured in decades and thousands of lives. That was the promise of SUBSAFE, that no crew would repeat Thresher's fate because every lesson had been learned, documented, and institutionalized. 10th April 1964, Arlington National Cemetery, Virginia. 1 year after Thresher's loss, the Navy dedicated a memorial to the 129 men who died. The ceremony included families, submarine force leadership, and shipyard workers from Portsmouth. Vice Admiral Elton Grenfell, Commander Submarine Force Atlantic, delivered remarks. "They went to sea knowing the risks," Grenfell said. "They did their duty with courage and skill. We honor them not only by remembering their sacrifice, but by ensuring that the lessons from their loss make every submarine that follows safer." The words were more than ceremony. By April 1964, SUBSAFE had transformed submarine construction and operation. The program was producing measurable results. Submarines completing certification were diving to test depth and deeper, with documented safety margins. Systems functioned as verified. Quality control procedures caught defects before they reached sea. But the human cost remained. 105 crew members, 17 civilian technicians, 7 observers, each had family, friends, and futures lost on 10 April 1963. The memorial at Arlington provided a place for remembrance, but it could not restore what had been taken. Among the families present was Mrs. Barbara Harvey, widow of Lieutenant Commander John Harvey. In a brief interview, she said, "John believed in the Navy's mission. He believed in his boat and his crew. I want to believe that something good came from their loss." Something good had come, though the exchange was bitter. SUBSAFE had emerged directly from Thresher's destruction. Every standard, every procedure, every verification requirement traced its origin to failures identified in the investigation. The program was built on hard-won knowledge, knowledge paid for with lives. The Navy also established policy regarding reactor safety in lost submarines. Both Thresher and Scorpion carried nuclear reactors that would remain on the ocean floor indefinitely. The Navy committed to periodic monitoring of both sites, using deep-sea sampling to verify that radioactive materials were not leaking into the water column. The first monitoring mission occurred in 1965. Research vessel Mizar returned to the Thresher site with water sampling equipment. Technicians collected samples at various depths above the wreckage, analyzing them for cesium, strontium, and other fission products. Results showed activity slightly above background, consistent with residual contamination from the coolant release on 10 April 1963, but well below levels that would present environmental hazard. The reactor core itself remained sealed within the crushed pressure vessel and primary shielding. Monitoring continued annually, then every 5 years. Each survey confirmed that the wreckage presented no significant radiation hazard. The Navy's transparency about reactor monitoring contrasted with earlier practices. Before Thresher, reactor accidents were classified and discussed minimally. After Thresher, the Navy recognized that public confidence required openness. Monitoring data was declassified and made available to independent review. This shift reflected broader changes in how the Navy managed nuclear operations. Naval Reactors Branch, under Admiral Rickover's leadership, had always emphasized technical excellence. After Thresher, that emphasis extended to include institutional discipline, documented verification, and accountability. Rickover himself testified before Congress in 1964, defending the SUBSAFE program's costs and scope. "We cannot afford to assume that complex systems will work as designed," he said. "We must verify, we must test, we must document. The alternative is measured in lives." Congress approved funding for SUBSAFE implementation across the fleet. The program became a permanent element of submarine force operations, with dedicated personnel, facilities, and authority to halt work when standards were not met. By the late 1960s, SUBSAFE had matured into a comprehensive system. Every submarine under construction was built to SUBSAFE standards from the keel up. Every boat in service had been retrofitted and certified. The submarine force had transformed from an organization that trusted its engineering to one that verified it. The change was visible in every shipyard. Inspectors prowled construction sites, checking welds and reviewing records. Workers understood that quality was not negotiable. Managers knew that schedules and budgets were subordinate to safety. The culture had shifted fundamentally. That shift was Thresher's legacy, not just procedures on paper, but a commitment lived daily by thousands of people who would never go to sea but whose work kept submarines safe. 1970, Electric Boat Division, Groton, Connecticut. USS Los Angeles, SSN 688, the lead boat of a new class of attack submarines, moved through construction. Los Angeles represented the next generation, faster, quieter, and deeper diving than any previous design. She also represented the first class designed from inception under SUBSAFE standards. Every component on Los Angeles carried documentation. Valves had material certifications tracing steel composition to the mill heat. Welds had radiographic inspection records showing complete penetration. Piping systems had pressure test results confirming no leaks at twice operating pressure. The paper trail for a single submarine filled a warehouse. A quality assurance inspector working on Los Angeles later described the process. "You couldn't install anything without documentation. Every valve had a tag showing. It had been tested. Every weld had a report. If the paperwork was missing, you removed the component and got one with proper certification. No exceptions." This was SUBSAFE in practice. Not dramatic, not visible, but relentless. The program worked by eliminating uncertainty. If a valve was supposed to hold 3,000 pounds per square inch, it had been tested to 6,000. If a weld was supposed to be defect-free, radiographic images proved it. If a procedure required 3 inspections, 3 signatures appeared in the records. The philosophy extended to reactor systems. Naval Reactors Branch had developed stringent quality standards that paralleled SUBSAFE. Reactor components required material certification, dimensional inspection, and performance testing. Pressure vessels received ultrasonic inspection across 100% of their surfaces. Coolant piping was all welded, with every joint documented. Los Angeles' S6G reactor, manufactured by General Electric, embodied these standards. The reactor core contained approximately 193 fuel assemblies, each containing uranium dioxide pellets enriched to military specifications. The assemblies were arranged in a cylindrical core approximately 4 feet in diameter and 6 feet tall. Control rods inserted between assemblies regulated the fission reaction. The primary coolant system circulated approximately 300,000 pounds of water per hour through the core, removing 165 megawatts of thermal energy. That heat drove steam turbines producing 35,000 shaft horsepower, enough to propel Los Angeles to speeds exceeding 30 knots submerged. Every aspect of the S6G design reflected lessons from Thresher. Coolant pumps had redundant power supplies. Emergency cooling systems could inject borated water through multiple independent paths. Instrumentation monitored core temperature, pressure, and neutron flux with redundant sensors. If any parameter exceeded limits, automatic safety systems would scram the reactor within seconds. Los Angeles also featured improved emergency blow systems. Thresher's investigation had revealed that ballast tank blow capacity was barely sufficient at test depth. Los Angeles carried larger compressed air banks and more robust piping, ensuring that even with flooding in multiple compartments, the submarine could surface. The pressure hull itself was constructed of HY100 steel, higher strength than Thresher's HY80. This allowed deeper operating depths while maintaining structural margins. Every hull plate received ultrasonic testing to verify uniform thickness and absence of internal defects. Welders passed stringent qualification tests before working on hull construction. Every hull weld received radiographic inspection. When Los Angeles launched in April 1974, she carried documentation tracing every critical system to source materials, manufacturing processes, and inspection results. The submarine was not simply built, she was proven. Sea trials in 1975 confirmed the design's performance. Los Angeles reached test depth smoothly. Her reactor operated flawlessly. Systems responded exactly as predicted. The boat was fast, quiet, and capable, everything the Navy required. But more important, she was safe. SUBSAFE certification verified that every potential single-point failure had been eliminated. Redundant systems ensured that any casualty could be managed. Procedures existed for every conceivable emergency. The submarine could survive mistakes, equipment failures, and external damage that would have sunk earlier boats. Los Angeles became the first of 62 submarines in her class, the largest single submarine class ever built. Each boat was SUBSAFE certified, each operated safely for decades. The class logged hundreds of millions of submerged hours without a major casualty. That record was Thresher's gift to every sailor who followed. 1986, Naval Research Laboratory, Washington, D.C. Scientists completed analysis of 23 years of monitoring data from the Thresher site. The results confirmed that the submarine's reactor posed no significant environmental hazard. Activity levels in water samples remained near background. Sediment samples showed localized cesium-137 concentration consistent with decay of coolant released in 1963, but levels were far below regulatory concern thresholds. The monitoring program illustrated the Navy's long-term commitment to environmental responsibility. Every survey produced public reports. Independent scientists reviewed the data. The transparency contrasted sharply with earlier Cold War practices of secrecy surrounding nuclear operations. But the environmental legacy was secondary to the human legacy. By 1986, the submarine force comprised more than 140 boats, everyone SUBSAFE certified. 3 generations of submariners had trained under protocols established after Thresher's loss. The program had become so fundamental that junior officers learned about it in basic training, understanding that their safety depended on procedures traced directly to April 1963. The success was quantifiable. Between 1963 and 1986, U.S. submarines had conducted more than 12,000 deep dives, defined as exceeding 800 feet. They had operated in every ocean, under Arctic ice, in waters where Soviet submarines hunted them. They had experienced equipment casualties, fires, floodings, and collisions, but no SUBSAFE certified submarine had been lost. That record represented more than luck. It represented design margins, quality control, training, and discipline. It represented thousands of people, engineers, welders, inspectors, operators, doing their jobs correctly every time. A submarine force commander in the 1980s noted, "SUBSAFE is expensive, it slows construction. It requires documentation that seems excessive, but it works. We know it works because submarines that follow SUBSAFE standards don't sink." The program's influence extended beyond the US Navy. British, French, and Soviet submarine forces studied SUBSAFE principles, adapting them to their own construction and operational practices. The Soviet Navy, after losing multiple submarines during the Cold War, implemented rigorous quality control standards modeled partially on SUBSAFE. The commercial sector also benefited. Deep-sea submersibles, offshore drilling platforms, and underwater habitats adopted quality assurance practices derived from SUBSAFE. The principle of documented verification, that safety claims must be proven, not assumed, spread across industries where human life depended on engineering integrity. But for the families of Thresher's crew, the program's success could never fully compensate for their loss. The memorial at Arlington remained a place of pilgrimage. Each year on Teen April, submariners gathered to remember the 129. The ceremony included reading the names, a roll call that no one answered but that everyone present heard. Among those who attended regularly was a former Portsmouth naval shipyard worker who had been involved in Thresher's construction. He never missed the anniversary. When asked why he came, he said simply, "I want them to know we learned. We didn't let their sacrifice be for nothing." That sentiment captured the moral core of SUBSAFE. The program existed not just to prevent future losses, but to honour past ones. Every certified submarine, every verified system, every documented inspection was a memorial as real as the bronze plaque at Arlington. The Navy also maintained operational security about current submarine capabilities. Test depths, operating limits, and specific system details remained classified, but the principles of SUBSAFE were public: quality standards, testing requirements, verification procedures. The submarine force could be transparent about how it ensured safety without compromising operational effectiveness. By the late 1980s, SUBSAFE had operated for a quarter century. The program had survived budget pressures, schedule demands, and occasional arguments that its standards were excessive. But the record spoke for itself. Safety was not assumed, it was verified, and verification worked. 10 April 2013, Naval Submarine Base, New London, Connecticut. The submarine force marked the 50th anniversary of Thresher's loss and SUBSAFE's founding. The ceremony included senior leadership, submarine veterans spanning 5 decades, and family members of Thresher's crew. Admiral John Richardson, Director of Naval Nuclear Propulsion, addressed the gathering. SUBSAFE is not a program, it is a commitment that we will not send our sailors to sea in boats that are anything less than proven safe. That commitment was born here, 50 years ago, from the loss of 129 shipmates. We have honoured their memory not with words, but with a perfect record. No SUBSAFE certified submarine has ever been lost. The statement was factual. 50 years, tens of thousands of operations, millions of hours submerged, hundreds of deep dives annually. Not one SUBSAFE certified boat had sunk. The record reflected extraordinary institutional discipline. SUBSAFE had survived leadership changes, budget cuts, operational tempo increases, and technological evolution. Submarines had grown larger, faster, and more complex. Construction methods had modernized. Computer systems had replaced manual controls. But SUBSAFE's core principles remained unchanged. Document everything, verify everything, and accept no compromises. A senior chief petty officer who had served on multiple submarine classes, described the program's impact. "When I walk through a boat, I know that every valve, every weld, every system has been checked. I know because someone signed the paperwork, someone inspected the work, and someone verified it met standards. That knowledge matters when you're 1,000 feet down." The confidence was justified. By 2013, the submarine force operated Virginia-class boats that incorporated advanced automation, improved stealth, and enhanced capabilities, but they remained subject to the same SUBSAFE standards established in 1963. Inspectors still verified welds, engineers still documented materials. Quality assurance personnel still had authority to halt work that did not meet standards. The program had also adapted to changing technology. Modern submarines carried sophisticated electronics, fiber optic networks, and computer-controlled systems that had not existed in Thresher's era. SUBSAFE standards evolved to cover these systems, ensuring that electrical failures could not compromise watertight integrity or buoyancy. The cost of SUBSAFE compliance had grown as well. A Virginia-class submarine required approximately 18 months longer to build than would be necessary without SUBSAFE verification. The documentation for a single boat filled shipping containers. The inspection and testing added hundreds of millions of dollars to construction costs. But the Navy never wavered. Safety was not negotiable. The alternative, another submarine lost, another crew dead, another investigation revealing preventable failures, was unacceptable. The 50th anniversary also prompted reflection on lessons that extended beyond submarines. SUBSAFE demonstrated that complex, high-risk systems could be operated safely through rigorous quality control, documented verification, and institutional discipline. The principles applied equally to nuclear power plants, aircraft, spacecraft, and medical devices. Industries worldwide studied SUBSAFE as a model for managing risk. The program showed that safety was achievable not through perfection, but through systematic identification and mitigation of failure modes. No single person had to be perfect, but the system had to verify that each person's work met standards. The memorial service at the Thresher Monument included a wreath laying at sea above the debris field. Ships from Submarine Squadron 12 sailed to the site. At the precise coordinates where Thresher had imploded, they stopped engines. A ceremony was held on deck, with submariners in dress uniforms standing at attention as a wreath was lowered into the water. The wreath descended through 8,000 feet of ocean, carrying the submarine force's enduring respect for those who had gone down before. When it reached the bottom, it would rest near the scattered remains of USS Thresher, a submarine that had failed but whose failure had purchased 50 years of safety. 2025. Submarine Force Museum, Groton. The USS Thresher exhibit occupies a central gallery, surrounded by artifacts, photographs and documentation spanning 6 decades of submarine safety evolution. The centerpiece is Thresher's nameplate, a brass plate salvaged from the surface debris in April 1963. The exhibit traces the submarine's history from construction through loss, then follows SUBSAFE's development and implementation. Interactive displays explain quality assurance procedures, materials testing, and certification processes. Visitors can examine actual SUBSAFE components, a certified valve, a radiographic weld image, a material certification document, understanding how these mundane objects represent the difference between safety and disaster. The human dimension remains central. Photographs of Thresher's crew line one wall, each face representing a life lost and a family forever changed. Letters from crew members, written shortly before the final voyage, convey ordinary concerns and hopes. None knew they were sailing toward death. The exhibit also presents the investigation findings, the Court of Inquiry conclusions, and the SUBSAFE program charter. Visitors see how disaster drove reform, how loss purchased knowledge, how tragedy compelled institutional change. A video presentation features interviews with SUBSAFE inspectors, submarine commanding officers, and naval architects. Each describes the program's impact on their work. An inspector explains how a single missed defect can halt certification. A commanding officer discusses the confidence that comes from knowing his boat meets verified standards. An architect describes designing systems to SUBSAFE requirements. The exhibit includes statistics, number of submarines certified, hours of safe operation, dives completed, lives protected. The numbers are extraordinary. Since 1963, SUBSAFE has overseen more than 150 million hours of submerged operations. The program has certified more than 200 submarines. Not one has been lost. That record stands as Thresher's memorial, not bronze or stone, but operational safety sustained across generations. Every submariner who served on a SUBSAFE certified boat benefited from lessons learned on 10 April 1963. Every family spared the anguish of loss owes gratitude to the 129 who died off Cape Cod. The museum's final exhibit panel poses a question. What is the value of a perfect record? It answers with a quote from Admiral Hyman Rickover. The value is not statistical, it is human. Each submariner who goes to sea and returns safely represents the promise we made after Thresher, that we would do everything possible to ensure no crew suffers the same fate. Outside the museum, visible from the main gallery, submarines from multiple eras are displayed. USS Nautilus, the first nuclear boat, sits permanently moored. Modern attack submarines pass regularly, heading to sea or returning to port. Each represents decades of technological evolution, but each carries the same brass certification tags on critical valves, the same documented verification, the same commitment to proven safety. Visitors leaving the exhibit pass a simple plaque. In memory of USS Thresher, SSN 593 and her crew. Lost 10 April 1963. Their sacrifice made every submarine that followed safer. The words are quiet, factual, respectful. No hyperbole, no embellishment, just the truth. That truth has sustained the submarine force for more than 60 years. SUBSAFE works because people remember why it exists. The program persists because institutional memory remains strong. Every inspector who verifies a weld, every engineer who documents a test, every operator who trusts his boat does so, knowing that their work honours the 129. Thresher's crew did not die in vain. They died because assumptions proved insufficient and verification was lacking. Their loss taught the Navy that complex systems require not faith but proof. That lesson, applied rigorously through SUBSAFE, has saved thousands of lives. It remains the most valuable legacy a disaster can leave. Knowledge that prevents repetition